everyone. Today, it is our great honor to invite Professor Lee to give a seminar on the title, Light Extraction of OLED Display by Microstructured Film Attachment. Dr. Lee obtained his PhD degree in 2000 from National Taiwan University, and since 2003, he joined the faculty of National Taiwan University. His research interests include organic optoelectronic devices, display and lighting technologies, and solar cells. Now let's welcome Professor Lee.
Thank you, Highway. It's my great honor here to talk about something that we did for the OLED, and there's a big problem as well as the LED because the light extraction efficiency is not high due to the total internal reflection. And one special thing is we are not working on the device level, we consider about the display level. So you are not only consider about the light extraction, you also have to consider about the image quality, because for the display, sometimes you can extract the efficiency, but the image blur or image quality will degrade, so that is not acceptable. And I come from Taiwan, and Taiwan there are lots of the display companies, so very luckily we have some we have many collaborators from industry, so we also know some design rules, because for the manufacturer there are lots of the restrictions. So one of that is we can only use microstructure instead of the narrow structure, because narrow structure is not well established for some manufacturer. So here we use OLED display, and then we use a microstructure film attachment to improve the light extraction. So possibly they are not a very scientific seminar, but anyway, it's kind of engineering, and I hope we can just open for discussions. Okay, so if anything you want to discuss, we can interrupt anytime. Okay. So as my outline, I will first give some introduction, and we will show you lots of our results. We have working on this project for about 10 years, and have some projects. Many come from the Taiwan industry, so it's the different kinds of microlens array. So we change different, for example, different size, different height of microlens array at first time. Then we found OLED itself also affect the light stream efficiency. So these two affect each other. Then we try to do some layout design of the microlens array film. So we patent that. So for example, we have the large size or small size, or some place we put the microlens, some place no microlens. So we patent that. And we also try other configuration, for example, the cylindrical array film or trapezoidal. So that is the 2D structure design. And then we also found there's a black matrix, and they will affect some, that is used for the reduced ambient light, but actually they will have some effect on extraction efficiency. So not only the two-dimensional design, you have to consider about the three-dimensional design. So that's the main part of this talk. And also in the introduction part, I will introduce some of my other researches. So it's me. So from NTU, BS, PhD, then after 3 years in industry, then go back to NTU again. So it's all NTU. So I had visited Professor Wu's group 11 years before and 10 years before, and also Caltech and the Riverside about 4 years before. So that's me. Okay, so right now my research topic include two parts. One is for the OLED, and as we know, OLED is emerging display and lighting technology, and the lifetime efficiency is two important parameters. And the other is the solar cell. We have some organic solar cell, inorganic solar cell, especially CHGS, and we also have some hybrid solar cell. So that is two examples. One is we collaborate with chemists, so they have synthesized universal host material, so we can fabricate for the blue, green, or red OLED. And if you know that, typically there's an upper limit about that's roughly maybe 20 to 30% in external quantum efficiency due to the total interreflection. So actually, those values are pretty high, close to the theoretical limit. And about the efficiency, we just published a paper 2 weeks before in SID. We use some AH-missed assist host, so we can use some material by engineering the device, so that improve the lifetime almost double it.
What's the required T95 for actual display?
For the T95 lifetime, yeah, right. So for example, for the 2000 and for 50 is typical. And but because
50 hours is sufficient?
Yeah, because if you read. Because during the normal application, the luminance is lower,
yeah.
So the lifetime is longer. Yeah. So, but this was fabricated in the experimental machine, not a mass production one. So there's a difference. Typically, they will have about 3 times or maybe to 1 order difference in lifetime performance.
Better.
Yeah, right. For the mass production, that's cleaner, and their base pressure is lower, and the material is pure, so typically it's higher, much higher. Yeah, but this is the baseline. Yeah, so because it's also the collaboration with industry, so that is right now used for the product. So which means we can improve the lifetime performance by almost 2 times. With just some modification in their structure.
What's the wavelength?
The wavelength is about 4 peak at 470, and 4 with and half maxima around for the material itself around 70, but you can use some cavity to reduce to lower 50 something. Yeah, this one is the not the fluorescence material. It's we call the TTA material, triple annihilation material. Yeah, we will talk about that tomorrow in the class. But yeah, anyway, it's the commercial used material. Yeah, actually we have some other experimental results, and right now they can achieve over 200 hours. So 4 times improvement already. Okay. So the other thing is, as we know, for example, for the LED and OLED, it's similar, but LED has a much for the LED, red, green, blue, for the blue one has a longer lifetime, but for the green one has the shorter lifetime. But for the OLED, it's different. Because for the OLED, for the organic material, if the wavelength is shorter, energy is larger, so that will reduce the lifetime. So one criteria for the OLED is to lower the driving voltage. So we try to develop this topic is sub-bandgap material, a sub-bandgap mechanism, which is we can use, for example, 2.2 volts to generate the blue emission. Is about 2.76 electron volts. It corresponding to 450 millimeter by low voltage. So that is potentially possible to improve the lifetime as well. So yeah, so right now we are just writing the patent about that. And interestingly, we found there's a blue and a yellow, so actually it's white. Okay, so we also do some solar cell applications. It's also collaborate with some chemists. So for example, you can see the blue color, green color, and red color, and connect together. We call that it's a donor, acceptor, acceptor. We call it a DAA material. And this kind of a DAA material, they have some dipole inside, so we can change some different ligands. For example, here is a phenyl, and we can change to the silophene, on the phenyl to silophene here. And here's the sulfur will be replaced by the oxygen. And we can tune their electrical and optical characteristics. For example, their absorption band will change, and also their hormone level will change as well. So, for example, if that is phenyl versus silophene, then for the phenyl one, they will have a better VOC. For example, that is CPB. They have the lower hormone level. So typically, if they have the deeper hormone level, then the VOC will be better. But if you replace the phenyl to silophene, then the absorption has a redshift. So if the spectrum redshift, which means you can absorb more light, so they will have the better JC short circuit current. So if you see this direction, so it's the benzoyl diazo, it's the sulfur changed to the benzoyl also diazo, then we have the better VOC and the better absorption. So from the chemists, they say, oh, this one, if you use the silophene and the oxygen here, that will be the best. So we received this material and we fabricated devices, and we found, wow, yes, for the VOC, it's related to the hormone level. Yes, this one is best. Yeah, but okay, let me see everything. So VOC trend is similar to the chemists predict, and the JC is the same. Is not changed too much because we have a very strong absorber in C60. So JC was determined by the absorber material. But we can see the efficiency here. This one is best. And actually, it was expect this one should be the best. So the major difference comes from the fill factor. So right now, although the JC and VOC, which can be predicted when you synthesize the material, but fill factor is still a mystery. So we have some measurement and some theory about the fill factor, and that is related to the organic material packing. So that is part of our organic solar cell research. And we also do some research in the inorganic solar cell, especially the CIGS, copper indicating selenite. So we use we call the top trialkyl sulfide on top S to passivate the surface. Because during the fabrication of the solar cell, sometimes we have to do some interconnection. So we need to scribe it and make some interconnection. But this kind of scribing results in a defect, so that will reduce the efficiency. So as we can see here, if we intentionally scribe something here, then that will result in the loss in VOC. So the black line is before scribe, so that's good. But after scribe, you see the loss in the JC. But we can use a top S, just one drop here, to make up the defect, to passivate all the defects, so we can recover some. So, which means they will have about 10% improvement in the efficiency for this kind of CIGS. So that's for the inorganic solar cell research. And we also do some hybrid solar cell, and we investigate the so-called single division mechanism. That is in some organic materials. For example, if you put two molecules together, and one is absorbed the photon, so this one is excited to the S1 state, and the other is on the ground state. So if this organic material, they have the very low triplet energy. So it is possible from one singly acetone, and they will share the energy to the neighboring molecule. So they will have two triplet acetone. So it's kind of multi-acetone generation. So for example, we can use for example, tetrazine to absorb the maybe blue line or green line, and generate two acetone with longer wavelengths. So that is possible to surpass. This is the Schottky crystal limit. That is the upper limit set by 50 years before. So with different bandgap material, they have a theoretical upper limit of the power conversion efficiency. And by single fission, it's kind of multi-acetone generation. We can surpass this limit. Yeah. So we studied this kind of single fission dynamics, and especially the singly acetone and triplet acetone. So it's the transition PL study in the 2 nanosecond range and the 2 microsecond range. So with different thickness of our organic material, and we found with the thinner one, and they have the stronger singly. That is the singly to triplet, the triplet back to the singlet to give the light, and that is enhanced signal. So that is we call the caging effect, because that is thinner, so the triplet will easy to recombine and find each other and give the singlet. If that is very thick, and they will go away and they will not give the light, so the intensity is lower. Okay, so that is some research topic what I'm doing. So it's very diverse. OLED, solar cell, organic, inorganic, like that. And so any question? Anything you want to know in detail? Yeah, okay, so let's move on. So here is some research also supported by the Innolux before 2 years before, and possibly related to the topics we talked today. So I just show you some results. So we know that mosaic can reduce anti-reflection coating, so that is very important for the display. So about 2-3 years before, we published this paper in SID, and that is the Microstructured, that is mosaic. So they can reduce the reflection, so low reflection. So at that time, people say, oh, we want to fabricate on the flexible display. So how about to make made on a flexible substrate? We say, okay, yes, great. And because that at the outside of the display is a touch panel. So we want, because it's a touch panel, you have to touch all the time. So we want it has a characteristics of self-cleaning, so that it's not dirty. And a high hardness, which means it's scratchable, so you can protect your device. And of course, because that's a display, so it should be low haze. Okay, so let's see why the reflection is important for the display, because if there's no air coating and you can see some ambient reflection, so the image will wash out during under the high ambient. So that's so we can use MOSI, this kind of structure. That's not our work. That's by the MIT's work. Yeah, but that's by glass, so that is not flexible. Okay, so how do we do this this surface? So first, we have the nanostructure template. So this is the SiO2 nanosphere. So we use a spin coating on the substrate. This substrate can be glass or silicon. You have to tune carefully. So there will be self-assembly monolayer of the silicon sphere. And on the other substrate is a flexible substrate, for example, the PT. Then we have some hard coating. For example, for your protection layer on your mobile phone, that is the hard coating. And they have very good hardness, maybe 7H, 8H, or 9H. Okay, so we just press it, oops, and have the UV curing. Then when you move out, then that's kind of similar to MOSI. So that's our nanostructure MOSI. So first of all is the template. We just been coating the silicon dioxide nanosphere and drying. So there will be self-assembly, monolayer, close-packed nanostructure. Then we use the CFX here that will be easier when you release to your PET subject. So you put here, then release that, but there are still some SiO2 nanosphere will stick on here. So we use a HF dip, so they can etch in this particle. So that is the ACA image for the that is on the template. So then you can transfer to the our flexible subject. So you can see actually that is a hole, something like a hole, and the dimension is about 125 millimeter. So you can press different compressive stress. So if that is ultra low, sorry, it's not really it, but that's kind of hemisphere. But after some pressure, then that is the whole circle, like that. So that's the range is pretty large, not very difficult to fabricate. And there are some residues when you remove that. So you use the HF dip, then you can have a beautiful holes over there. So how about optical property? So we can see it's the transmittance. We fabricate different compressive stress, and anyway, that can achieve about 96, 97, because we only do for the one side. So for the other side, there are still 4% reflection. So for the reflectance, that's between 0 and 1 for the wavelengths. And we also measure the haze, and the haze a little bit lower, a little bit higher, sorry, to maybe 2 or 3. So we have a little bit concerned about the image quality. So we put our film on the real display, and we based on this equation, and we take the digital camera, take the photo by digital camera, and we compare the image quality factor from 1.0 means 100%, and that's a reference. And our image quality is 0.97, so that's 97%. So that's almost indistinguishable by human eyes. So we also use the pencil harness to test. And for the PET substrate, it's very soft. And if we use a hard coating, this hard coating, because we need to have the hard coating to be flexible. So if that is 9H or 8H, we can tune the composition. We have some collaboration companies. They can tune to the 8 or 9H, but that will fail when you do the flexible experiment. So they say, oh, 6H is safe. So we use the 6H for the planar, and you use some structure, it degrades to about 2H or 3H, but it's still not too bad. And how about flexibility? We can down to the 8 millimeter in diameter, so that's no problem. So that is what we can have. So the reflectance, the minimum is about 0.5, and average is about less than 1. And the haze is a little bit, maybe we said over 1, but still okay in terms of the image quality. And pencil hardness is okay, not too bad, but it's possible to tune to a higher level or so. And flexibility is okay. Okay, any question?
What kind of material for this hard coating?
Material, okay. It's kind of a mixture of the acrylic and the polymer with different composition. Yeah, but the detail, yeah, that's the secret of the company, but it's the acrylic base.
Fujifilm this year also reported the similar structure, the performances. How does yours compare with Fuji's in terms of?
Oh yeah, right. They have the spraying process, and there's a binder to keep the ball on that.
Right.
So they can have the larger size sphere, maybe 1 micron or so. That is for anti-glare, and for the smaller one, that's for the anti-reflection. Yeah. So yeah, they have different pros and cons. And for us, because anyway, when we purchase the mobile phone, the first thing is to buy a protective film. So we are pretty compatible with the protective film. And I'm not quite sure about the scratchability. So I saw some, because that is the industry project. So all of our measurement was based on the industry standard. So the company gave us the standard. You have to follow the same process as they did. But I saw they have something related to the hardness. I think maybe this one is some different, but I'm not sure about their value. Yeah.
So what's the typical hardness of the protective film on our phones?
Yeah, you can buy from the website. You can check. Right now, you can purchase maybe 9H. Yeah, but that is not flexible. Yeah, you have to compromise. Yeah, for every properties.
And what's the solvent you use for disperse the SiO2 nanosphere?
Solvent? That's provided by also another company. Yeah, so they just give us a bottle. There's a nail spear. We just sprinkle. So they have the solvent inside already.
Oh.
Yeah, because that's industry project. So they provide us all the materials.
Mm-hmm.
Yeah.
Besides scratches, what if we have oil or greasy solvent or liquid, and which is attached to the this nanoscale surface. Will that be how do you clean it?
Oh,
You
you
use
are,
a solvent? I mean, besides the mechanical scratches, what about the moth eyes resistivity to like a chemical?
sorry, I forgot to mention about this. We have the water contango, so that's water. And so actually we have some other anti-fogging coating on the top.
Yeah.
It's the alkyl fluorine coating, something like that. Just sprinkle. So the water contango is pretty good, but for the oil, maybe not so good, but acceptable. And because this layer is pretty strong, I mean the hard coating layer is pretty strong, because we can use the HF dip and there's no harm. So I say that they can resist the typical chemicals. That will be no problem.
Okay, good.
And what else? Yeah, okay. Besides, actually for the nail structure, they have the advantage itself is they have the better contact angle. So for example, if that is a nail structure itself without any treatment, they can have a very good contact angle, something like that. So that's the nature for the nail structure. Yeah, looks like they love this. They love this idea for the industry. Okay. So that's a flexible, low reflection, low head, self-cleaning, high hardness. Yeah. So it's something we achieve. Okay? Yeah.
I remember for the Fujifilm, their reflectance can be as low as below 0.5%, maybe 0.2% for the reflectance. And I'm just wondering the structure of your microstructure, for example, the diameter of the particles. Yeah, I mean the size has been optimized, or just
No, we don't we did not optimize, because at that time they said, below 1 is good enough. Yeah, so we just below 1. But we just demonstrate kind of the methodology to fabricate this kind of, so that is doable in experiment. But of course we can optimize for example, the diameter of the nail sphere, or even, because this kind of nail crystal grows, some people use some different size, different shape. So it is also possible to have different shape if you want. Yeah, I believe it is possible. Yeah. So what we demonstration is kind of the fabrication process, and that is possible for the mass production. So they even think about, for example, you have the, when you have the, there's a roll-to-roll process. If you have a very, you have the self-assembly, large area one, it's a donor fin and transfer to the other one, something like that.
here your template can only be used in wax, right? Because you will leave some nanoparticles on the substrate.
Mm-hmm.
So you will need a new template next time.
Yeah, right. So you need another foil on your roll-to-roll. So you have to make this self-assemble nail crystal first, then use as the donor fin, something like that. But if we can fabricate some mold and solve the problem of the sticking issue, so that is possible. So there's some protrusion and just you can use that for a long time, possibly. Yeah, just a demonstration of the experiment, but not optimized in the optical properties. Yeah. Okay? So that's a typical example to collaborate with industry. You must have that is doable during the mass production from every aspect. Yeah, but just prove a concept of something like that. Okay. So let's move on. Okay, to the extraction efficiency. So that is a collaboration with 3 groups. One is me. We have the display device technology lab. That was not named by me, by my student. So this is DDT. But it's not toxic. So another one is Professor Lin, also in NTU, is the display optics lab. So they are he's the expert in the optical design, simulation, lots of the simulation tools developed. And Professor Wei, we are colleagues when I was in the industry. So he is pretty good in the microstructure, nanostructure design and fabrication. And he's in the National Donghua University. He's the microforming lab. So we have collaborated for more than 10 years, and we have many projects, mainly from the Taiwan industry. It has some papers, conference, patents, something like that. Okay, so for the OLED, actually the coupling efficiency is only here, about 20%, and there are some substrate mode in your, for example, glass substrate, and your waveguide mode. Waveguide mode means in the organic material and your electrode, for example, ITO indium tin oxide. So remember that here's CREOL, right? So for the light go to the high refracting index places. So for the substrate, for the outcouple is air, refracting index equals to 1. For the substrate, refracting index is about 1.5, that is glass. For the waveguide, for the organic material and ITO, refracting index is about 1.8 to 2.0. So here, actually there is the highest refracting index places, so many nice check here. And also there are some surface plasmas, because for the organic material, the thickness is only 100 nanometer, 200 nanometer, so your emission dipole is very close to your electrodes, especially the metals, so they are very strong surface plasma. But if you increase the thickness of your binding layer, then the plasma contribution will decrease. And there are also some absorption from materials, non-radiative loss or electrical loss, something like that. So the efficiency, extraction efficiency is pretty low, typically. So we have to, what we want to do is from the substrate mode, waveguide mode, surface plasma mode. So from the substrate mode is we can put some micro lens here, so some light rays. Here is the total internal reflection, so right now they can be extracted. So for the waveguide mode, we can use, we call that, right now typically we use a high index substrate. So for example, we can replace the lower index to the higher index, maybe 1.78, 1.8, something like that. So reduce the total internal reflection in this interface, then we can use some lens to couple out the light. So they can achieve maybe over 100 microwatt and 1000 nits. The other thing is the plasmonic mode. And the plasmonic mode can use the nanostructure corrugated, especially in the metal layer. So that is possible to have the phase matching condition to extract the plasmonic mode out. So that is possible right now for the EQE over 63% by couple out this surface plasma mode. So let's think about application. There's two main application for the OLED. One is for the lighting, the other is for the display. So for the lighting, that is fine, but for the display, we have to consider many things. For example, you have to consider about your TFT. So is that a button emission or tie emission or so? So it's some fabrication yield, and so typically the industry, they don't want to have the corrugated structure inside the device. Outside is easier because you just attach that, but inside that is not easy because you have to consider about TFT process. And how about high-density substrate? Sometimes that is not preferred because for the TFT process, they have some special requirement for the your glass. For example, they want the alkaline-free glass because alkaline will diffuse into your TFT and your on-off ratio will degrades. So what we can do is to put something outside. So that's our restriction to the OLED display when you talk about that. Okay, so that is the illustration. So we have, if that is a display, you have to consider about the several pixels because there are some possible image blurring. So if we have 1, 2, 3, 4 different rays, if that is the planar, then you can see here is the total internal reflection over here. So if you put some micro lens array, you can see here, you can extract the light out of the device, right? But there are several questions. The first one is, you can see the ray 1. Ray 1 can goes out, but right now if you put the micro lens, it just goes back. So sometimes, because for the smaller incident angle light, you don't need micro lens. Actually, you don't need that. So actually, sometimes you don't need micro lens here. And the second thing is, if you see the ray comes from here, you will say, oh, it should come from this pixel. So that is image blur. So that will have some problem. So we found, oh, we should pattern it. So for example, here the light can goes out, so we don't need micro lens. So just remove the micro lens, and so we can have this light rays. So maybe in the boundary, so still acceptable. Yeah, and the other thing is, during the mass production, we have to consider about the gap. There is a minimum requirement of the gap. So for example, 2 micrometers is your limitation. So you cannot have the 1.5 micron, 1.1 micron. It's not acceptable. So when you have the higher and higher density, I mean higher PPI, then you will have the fewer aperture ratio. So we said, okay, so why not, actually we just need some non-planar structure. So we can use the slope over here. So we can extrude the light over here, and extrude the light over here. And that is, if we extract this light, and that will be a serious blur. So we just block here. So that's the trapezoid array fit. So that's the planar micro lens, pattern micro lens, and the trapezoid. So I finished. Any questions?
So, how do you fabricate trapezoidal pattern?
Oh, we can jump. Okay, great. So Professor Wei is the expert. So anything we design, and he can think about the fabrication. So it's a good team because we have some simulation, and we have some device, and we have some fabrication. So that's the fabrication flow for the trapezoid. And first, we use a silicon wafer and a photoresist, and that is called a diffusing lithography or something like that. Anyway, we use a mask, and upon the mask, we put a diffuser. So during the UV light irradiation, so there's a slope over here, okay, onto your photoresist. So after the develop, when you irradiate the light, that will be washout, and for the top surface, the exposure dose is higher, so they will have this kind of slope. So we have this kind of the mode, then we transfer to the PDMS, then after transfer to the PDMS, then we transfer to the PNNFE. So that is on the PET substrate, so that will be the flexible trapezoid. So we have the SCM picture, something like that. And we can tune the angle from 15, 25, yeah, like that. Okay?
Can you make this angle sharper?
Yes. Sharper is easier.
Oh, sharper is easier?
Yeah, because it depends on the diffuser
Okay.
you use.
Yeah.
Yeah. If you don't use a diffuser, then that's 90 degree, almost 90 degree. Yeah. So depends on your scatterance of your diffuser.
What is the thickness of your microstructure?
Thickness. We can tune. Oh, it's too small. For here it's 20 micron, and typically we can have from several micron to around 20 micron, 30 micron. That is okay. Yeah. And actually, right now we are doing some Microstructured. Yeah. For the typical photoresist, that is micron to several micron. If you want to go to the 10 micron, 20 micron, you need some special photoresist, but still achievable.
Can we fabricate the traploid structure reversed like this one? Because it's, for the top is short, the bottom is longer. Can we reverse the structure?
Yeah, this one.
Oh, yes.
Yes. We have we fabricate the photoresist on the silicon first, and we can transfer to the reverse one, then transfer it back.
Yeah.
Yeah, because if you have the PDMS mode, then you can fabricate a PET substrate maybe over 10 times. And from here to here, you can have 10 plates. So you can have that. If you fabricate this one, and you can have the 100. This one you can duplicate that much. Yeah, but that's not typical.
We would like to deposit ITO on the wall.
On the wall, oh, let me see. You mean this one?
Yeah. Not
Yeah, okay, that's
only on the island, not everyone, not continuous.
On this side.
Yeah,
only on this side.
I mean, yeah.
On the side over here.
Yeah.
Not on the bottom, not on the top.
We can talk afterwards.
Only on the side. Yeah, I believe that depends on your resolution. If that is several micron or so, I think that is possible. We can use this software.
Yeah, we can discuss afterwards.
Yeah, but anyway, we have this kind of technology. But we can do the ITO deposition. It's bothering. Richard, do you have something?
I want to ask whether you have experimental result for the crosstalk of this structure, like technical.
This one?
Yeah.
Okay. Yes. So we also use Lena picture. So if you so we use the image quality factor. So if that is the hollow microlensor, if you use the full microlensor array, then that will degrade the image quality to 72%, 0.72. So that's pretty bad. But if you use the so that is this one, planar one. Oh, sorry, this one. Oh, you can see the pixel. You can see the pixel, but you cannot see the pixel because that is blurred. So if you see the pixel, that is better. So if you use the pattern one, that is best. But if you use a trapezoidal, that is a little bit sacrificed. Yeah. But your extraction efficiency is better. So that is, for the white one is 64, higher than the pattern one, because you have the higher aperture ratio. So that's real display.
So the percentage there is in actual extraction efficiency.
Yes. Luminous. We use a luminous here. Yeah, so that's the industry measurement standard. So you have a mobile phone, you have a real panel. So you measure the luminous.
I have a question about the image quality. How do you quantify this quality of the image? I mean, what's the reference here?
Oh,
It's
okay.
0.91, 0.96.
So you can find in this paper, and because that's a signal process nature, and because actually your image or picture, when you transmit, and they are compressed. So when you compress, there are lots of some information. So they just want to know how bad of the image is acceptable. People cannot distinguish. So typically we need some reference. So typically that is no micro lens. So that is our reference. So Q means the image quality factor equals to 1, means 100. And that is, we took the picture under the optical microscope. So you see there's a black region over here. That is the TFT region. So that's the aperture ratio. So after then, you can put the micro lens on the display. Then you took again. Then they have you just transfer to the grayscale. Then they can calculate, because that will become many pixels. Then you can calculate that. So to the image quality, and then you can, of course, you can see under the microscope there are some blur. The blur is not black anymore. Something like that.
So which level is acceptable?
90.
90.
Yeah, 90%. Yeah, they say over 90% you can, it's indistinguishable. Yeah, we have worked on this topic for about 10 years, but right now I think this topic is more and more hot. So I just, use this topic. But I know you are the expert here, so we can skip lots of the slides. Just ask. Yeah.
I mean, for the angle of the trapezoid, which end, the small angle is better or large angle is better for the efficiency and for the image quality?
For the efficiency and the luminance.
Quality.
For image quality. It's a trade-off. Here's the bottom angle versus the luminance. So if that is 0, so that's planar, so equals to 1. And that increased the maximum around 20 degrees, and that will decrease sharply. Yeah. If that is, the angle is very large, so they will have the total internal reflection at the sidewall. So that cannot be very large. But if that is too small, that is similar to your planar. So that's optimized value. And also consider about that, you have to consider about the glass thickness, about the this gap between two pixels. So there are lots of engineering work to do. And that's, this simulation is based on the thick glass. I mean the 0.7 millimeter or so. Yeah. So there are lots of things you can play.
So I see you have fabricated both PET and PDMS. The main difference comes from the both substrate is the shape transfer quality or some other thing? Or they reflect?
We use a PDMS. We use a PDMS as a mode. So that's a reverse mode. So yeah.
So you have to align this to the pixel very well. So
Oh yeah, it's a good point. So for the trapezoidal, yes. And for the pattern microlens, yes. So for the trapezoidal, you have to align this to your pixel. And for pattern microlens, yes, we have to. That's a real OLED display. So we have to align very well with that. So that made the industry unhappy because they say, oh, that's not easy to align. So that's why we have another compromise solution. That is the cylindrical. So that's a symmetry one. So that's a cylindrical shape. So if this one is the subpixel, and we can put this direction or this direction, and we found it's still good. If the microlens array is about 80, they can a little bit higher, 82, 86, something like that. Oops. Yeah, but yeah, just between the pattern one and the planar one. So you can tune the shape, cylindrical or something like that. Yeah, actually, we have a pattern about the cylindrical, and finally, it was found in some real product of OLED display. They use this cylindrical. So they can, not only the luminous increase, they have some other advantage for the viewing angle.
Does Samsung use any internal or external methods to improve the light extraction efficiency? As you mentioned, they don't like the internal structure change, right? So but does Samsung use any external, like a film, your type of films or cylindrical lens to enhance the light efficiency?
For the
For OLED?
Yeah, I mean, I know. For the mobile application, no.
But for TV, they do? I mean, for... No, for mobile, means
Yes.
yes, for Samsung.
Yeah. Yes, you are right. Yeah. Because for the mobile, if you put some microstructure, because the human finger, they can touch maybe 10 micron. So if that is 50 micron, when you touch it, you will feel it. And people don't like that right now.
Mm.
Yeah. So that's another issue is if you do some external one, you have to consider there's a touch panel on the top. So you have to consider about the system. Yeah, but remember that this OLED panel is a touch panel, so there are something you can play. They use adhesive to combine these two together. But before the adhesive or after that, whatever, you have two substrates, you can play some game in between. Yeah. But they prefer the top side is the is flat. Yeah. And of course, you can put AG AR film on the top. So that's a whole system. And the other thing is about the internal light shading efficiency. Non-planar structure is not preferred, but they can do some planar structure for the better interference effect. That is some planar structure inside.
So, any more questions? Then I may have the last one. So, can we combine your AG or AR film with this nanostructure film, and then it may work? It may have two functions. One is for the AG or AR. The other one is to improve the efficiency, because both of them seem to have the similar nanostructure or similar structures. So, can we combine them together?
Yes, this is possible. I think there are, but because our MOSI structure is on the top surface and between the glass and the air, so possibly another way is to fabricate a structure combining narrow and micro together. I mean, you have the microstructure, but on the top surface of the microstructure, you have narrow structure.
Okay. So it's doable?
Yeah, basically, if there's a simulation really good, then good enough, then we can try to do that.
Okay. Thank you. So let's thank Professor Liu again. Thank you.